in the vast architecture of galaxies throughout our universe. Central bulges represent one of the most significant structural components that astronomers study to understand galactic formation and evolution. These densely packed stellar regions serve as the gravitational anchors for many galaxies, particularly spiral galaxies like our own Milky Way. Recent research has revealed that galactic bulges are far more complex and diverse than originally thought, with various formation pathways and structural characteristics that provide crucial insights into cosmic evolution. The following detailed examination explores the multifaceted nature of these central galactic structures, their properties, formation mechanisms, and their critical role in shaping galactic development across cosmic time. In astronomical terms, a galactic bulge refers to a tightly packed group of stars located within a larger stellar formation, almost exclusively describing the central concentration of stars found in most spiral galaxies. Historically, astronomers viewed these structures as elliptical galaxies that happened to have a disk of stars surrounding them. But high-resolution imaging from the Hubble Space Telescope has revealed a more complex reality about these central regions. A galaxy's bulge can be described as a central, roughly football-shaped structure composed primarily of stars, along with varying amounts of gas and dust depending on the bulge type. These structures represent some of the most densely populated regions of their host galaxies, containing stars that are often distinct in age and kinematic properties from those in the surrounding galactic disk. The bulge often serves as a critical component in defining a galaxy's overall morphology and evolutionary history, acting as both a record of past formation events and an ongoing participant in galactic processes. The prominence and characteristics of bulges vary significantly across the galaxy population, with some spiral galaxies featuring massive, dominant bulges, while others display minimal or almost non-existent central concentrations. This variation has led astronomers to develop classification systems based on bulge properties, which correlate with numerous other galactic characteristics, including star formation rates, mass distribution, and evolutionary pathways. Bulges often contain a significant fraction of a galaxy's total stellar mass, concentrated in a relatively small volume, creating a gravitational well that influences the motion of stars throughout the entire galaxy. This concentration of mass also creates conditions that favor the formation and feeding of supermassive black holes, establishing an intimate connection between bulge properties and central black hole characteristics that has profound implications for understanding galactic evolution. Modern astronomical research has established that galactic bulges fall into several distinct categories with different properties and likely different formation mechanisms. The primary classification divides them into classical bulges and pseudo-bulges, with a third category of boxy peanut bulges, sometimes observed in edge-on galaxies. This classification represents a significant evolution in our understanding, moving away from the earlier view that all bulges were essentially miniature elliptical galaxies at the centers of spiral disks. The recognition of these different bulge types has forced astronomers to reconsider theories of galaxy formation and evolution, as each type likely points to different formation pathways and evolutionary histories. The diversity of bulge types also helps explain why galaxies with similar overall morphologies can exhibit substantially different central properties and behaviors, including star formation rates and nuclear activity. Classical bulges most closely resemble the traditional view, featuring properties similar to elliptical galaxies with predominantly older stellar populations and more spheroidal shapes. These structures typically follow a Sérsic light profile and contain stars in mostly random orbital configurations, suggesting formation through dramatic events like galaxy mergers rather than gradual internal processes. The prevalence of classical bulges varies with environment, with about 2/3 of galaxies in dense galaxy clusters possessing classical bulges, compared to only about 20% of galaxies in less dense field environments. This environmental correlation provides strong evidence that classical bulges form primarily through interactions between galaxies, which occur more frequently in crowded cluster environments where galaxies regularly encounter one another. Pseudo-bulges, by contrast, show properties more aligned with disk galaxies than with ellipticals, featuring stars that orbit in an ordered fashion in the same plane as the stars in the outer disk. These structures often contain spiral patterns, dust, and ongoing star formation at a rate similar to those found in galactic disks, contradicting the traditional view of bulges as dead stellar systems. Pseudo-bulges frequently display nuclear rings actively forming stars at rates much higher than typically found in outer disks, as observed in galaxies like NGC 4314. The properties of pseudo-bulges suggest formation through secular evolution, the slow rearrangement of a galaxy's stars and gas in response to internal instabilities, rather than through the violent merging processes that create classical bulges. This difference in formation mechanism explains why pseudo-bulges retain many disk-like properties and continue to form stars actively long after their formation. Classical bulges possess distinctive characteristics that set them apart from other components of galaxies. They are composed primarily of older population II stars, which give them a characteristic reddish hue due to the predominance of longer-lived, lower-mass stars that have evolved away from the main sequence. The stars within classical bulges orbit in essentially random directions relative to the galactic plane, creating a three-dimensional spheroidal structure that contrasts sharply with the flat, ordered rotation of the surrounding disk. This randomized orbital structure results from the violent relaxation process that occurs during major galaxy mergers, when gravitational disturbances scramble the orderly orbital patterns that existed in the progenitor galaxies. The lack of significant amounts of gas and dust in classical bulges leads to minimal ongoing star formation, making them relatively quiescent in terms of stellar birth compared to both pseudo-bulges and galactic disks. Classical bulges typically display high central velocity dispersions, with measurements often exceeding 130 kilometers, reflecting the energetic, randomized motions of their constituent stars. This high-velocity dispersion has become an important observational criterion for identifying classical bulges, with studies showing that approximately 68% of classical bulge galaxies have central velocity dispersions greater than 130 km/s, compared to only 9.4% of pseudo-bulge galaxies. The mass distribution in classical bulges follows a Cirsic light profile, which describes how the surface brightness of the bulge decreases from the center outward. The age distribution of stars within classical bulges also shows a distinctive pattern in massive spiral galaxies, with the stellar population at the center typically being older than the stars at the edge of the bulge. This age gradient provides important clues about the formation history of these structures, suggesting an inside-out formation process during the early epochs of galaxy assembly. Pseudo-bulges differ fundamentally from their classical counterparts in both structure and stellar population characteristics. Unlike the randomized stellar orbits in classical bulges, stars in pseudo-bulges orbit in an ordered fashion in the same plane as the stars in the outer disk, creating a more flattened, disk-like structure that rotates coherently. High-resolution observations from the Hubble Space Telescope have revealed that pseudo-bulges are not devoid of dust, but rather show varied and complex structures, often including spiral patterns that resemble miniature versions of their host galaxies. These spiral structures within pseudo-bulges are typically 100 times smaller than the overall spiral patterns of their host galaxies, yet they dominate the light of the bulge regions in which they reside. The presence of these ordered, disk-like features strongly contradicts the traditional view of bulges as essentially elliptical structures, and points to formation mechanisms very different from those that create classical bulges. The star formation rates in pseudo-bulges typically mirror those found in disk galaxies, maintaining active stellar birth long after the bulge's initial formation. Many pseudo-bulges contain nuclear rings that form stars at much higher rates per unit area than is typically found in outer disks, creating localized starbursts that contribute to the bulge's growth and evolution over time. The central velocity dispersion of pseudo-bulges tends to be lower than that of classical bulges, with values typically below 130 km/s, reflecting the more ordered rotational motion of stars in these structures. Recent studies have proposed a mass-dependent criterion for distinguishing pseudo-bulges from classical bulges based on central velocity dispersion, recognizing that the traditional fixed threshold of 130 km/s does not adequately account for variations with galaxy mass. A third type of bulge structure, observed primarily in edge-on galaxies, displays a distinctive boxy or peanut-shaped appearance, sometimes featuring an X-shaped pattern when viewed from certain angles. The Milky Way's own bulge exhibits this boxy, peanut morphology, as confirmed by observations from the COBE satellite and later verified with data from the VVV survey using red clump stars as tracers. The WISE satellite has further confirmed the X-shaped structure of our galaxy's bulge, which represents approximately 45% of the bulge's total mass. These distinctive shapes are not actually separate types of bulges, but rather represent bar structures viewed edge-on, where the vertical thickening of the bar creates the characteristic boxy or peanut-shaped appearance. This understanding connects boxy, peanut bulges to the broader phenomenon of bar formation in disk galaxies, which occurs through secular evolution processes driven by gravitational instabilities within the disk. The identification of boxy peanut structures in numerous edge-on galaxies, including our own Milky Way, provides important evidence for the prevalence of bars in spiral galaxies and their role in driving secular evolution. These structures further demonstrate the complex, three-dimensional nature of what we collectively term bulges, highlighting the limitations of simple classification schemes and the need for detailed multi-wavelength observations to fully characterize galactic central regions. The X-shaped component observed in many boxy peanut bulges results from specific orbital resonances within the bar structure that push stars out of the galactic plane, creating the distinctive vertical extensions that give these bulges their characteristic appearance. The formation mechanisms for galactic bulges vary significantly depending on the bulge type, with classical and pseudo-bulges likely representing different evolutionary pathways. Classical bulges are thought to form primarily through major mergers between galaxies, particularly during the early gas-rich phases of galactic evolution. When galaxies collide, the violent gravitational disturbances throw stars into randomized orbits and can trigger intense bursts of star formation that rapidly build up the central stellar concentration. The merger hypothesis for classical bulge formation is supported by their higher prevalence in dense galaxy clusters, where interactions between galaxies occur more frequently. Recent studies of our own Milky Way suggest that its bulge formed primarily in a single burst of star formation more than 10 billion years ago, potentially triggered by the accretion of primordial material, or perhaps a merger with another young galaxy. Pseudo-bulges, by contrast, likely form through secular evolution processes that occur when a galaxy is left relatively undisturbed for extended periods. In this scenario, gravitational instabilities within the galactic disk cause stars and gas to gradually rearrange themselves, often forming structures like spiral arms and bars that can then channel material toward the galactic center. This inflow of material increases the density at the galaxy's center, building up a bulge that retains many of the disk-like properties of its source material. The prevalence of pseudo-bulges in relatively isolated field galaxies supports this formation mechanism, as these environments provide the long periods of isolation needed for secular processes to operate effectively. If secular evolution is indeed responsible for forming a significant number of bulges, it suggests that many galaxies have not experienced major mergers since the formation of their disks, contradicting some theoretical models that predict numerous mergers in recent cosmic history. The age distribution of stars within bulges provides additional insights into formation processes, with studies revealing that the stellar population at the center of the most massive spiral galaxies is older than the stars at the edge of the bulge, while in low-mass galaxies, the opposite pattern appears. Younger stars populate the center, and older stars reside in the periphery. This mass-dependent age gradient suggests a unified scenario for spiral galaxy formation, where both high and low-mass systems form through similar processes, but progress through these stages at different rates. High-mass galaxies apparently complete their central formation processes earlier and more quickly than their lower-mass counterparts, resulting in the observed differences in stellar age distributions. This finding aligns with the broader concept of downsizing in galaxy evolution, where more massive galaxies generally form their stars earlier and more rapidly than less massive systems. Most galactic bulges, regardless of type, are thought to host central compact masses, traditionally assumed to be supermassive black holes. These central black holes cannot be observed directly due to their nature, but substantial evidence supports their existence in both the bulges of spiral galaxies and the centers of elliptical galaxies. One of the most important discoveries in this area is the tight correlation between black hole mass and various bulge properties, suggesting a coevolutionary relationship between these seemingly disparate components. The M-sigma relation, which links black hole mass to the velocity dispersion of bulge stars, represents one of the strongest of these correlations, indicating that the processes governing black hole growth are intimately connected to those shaping the surrounding bulge. Other correlations involve the total stellar mass or luminosity of the bulge, the central concentration of stars, the richness of the globular cluster system orbiting in the galaxy's outskirts, and even the winding angle of spiral arms. The feeding of material into central black holes represents an important aspect of bulge-black hole coevolution. In barred spiral galaxies like NGC 1365, gas and dust are funneled toward the central region by the bar structure, simultaneously fueling both star formation in the bulge and feeding the central black hole. This process directly connects bulge growth through star formation with black hole growth through accretion, providing a physical mechanism for the observed correlations between bulge and black hole properties. Until relatively recently, astronomers believed that supermassive black holes could not exist without surrounding bulges, but observations have now revealed galaxies hosting supermassive black holes without accompanying bulges. This discovery suggests that while bulges and black holes typically evolve together, the bulge environment is not strictly essential for the initial seeding and growth of massive black holes. The kinematic properties of bulges provide crucial insights into their formation and evolution. Recent studies using integral field spectroscopy, IFS, have enabled detailed measurements of the rotational and random motion components of stars within bulges and their host galaxies. These observations reveal that galaxies hosting pseudo-bulges rotate faster than those with classical bulges at a given stellar mass. A difference attributable to both the more rapidly rotating disks in pseudo-bulge galaxies and the smaller relative size of pseudo-bulges compared to classical bulges. Interestingly, when examining the specific angular momentum, represented by the L parameter, versus ellipticity, A, relations for the bulges themselves, both types show similar patterns with little dependence on galaxy stellar mass. This similarity in intrinsic bulge kinematics, despite differences in host galaxy rotation, suggests complex interactions between bulge formation mechanisms and overall galaxy dynamics. Central velocity dispersion represents another key kinematic indicator that differs significantly between bulge types. Classical bulges typically display high central velocity dispersions, reflecting the random, energetic motion of their constituent stars. This property has led researchers to propose velocity dispersion thresholds for distinguishing between bulge types, though recent work suggests that these thresholds should be mass-dependent rather than fixed values. A new criterion based on the relationship between central velocity dispersion and galaxy stellar mass has been proposed for galaxies in the mass range of 10.4 log m 11.4, with the dividing line defined as log A0, 0.23 x log m 0.46. This mass-dependent approach recognizes that the kinematic properties of bulges scale with galaxy mass, providing a more nuanced framework for classification than simple fixed thresholds. Understanding bulge formation and evolution represents a critical component of our broader understanding of galaxy evolution. The tight connection between bulge properties and those of central supermassive black holes points to an intimate physical link between galaxy growth and black hole growth throughout cosmic history. This relationship suggests that the same processes driving the assembly of galactic bulges, whether violent mergers or gradual secular evolution, also regulate the growth of central black holes, creating the observed correlations between these components. The different formation mechanisms for classical and pseudo-bulges further indicate multiple evolutionary pathways for galaxies, with some experiencing dramatic transformations through mergers, while others evolve more gradually through internal processes. This diversity of evolutionary tracks helps explain the wide variety of galaxy morphologies observed in the universe today. The study of bulges in galaxies across different environments and mass ranges has revealed patterns that inform our understanding of cosmic structure formation. The observation that about 80% of field galaxies lack classical bulges suggests that many galaxies have not experienced major mergers since the formation of their disks, challenging some theoretical models that predict numerous mergers throughout cosmic history. Conversely, the prevalence of classical bulges in dense galaxy clusters confirms the importance of environmental effects in shaping galaxy evolution, with frequent interactions in crowded environments, leading to more merger-built structures. The finding that the Milky Way's bulge formed primarily in a single burst of star formation more than 10 billion years ago places our own galaxy's evolution in cosmic context, suggesting that it experienced its most significant formation events during the early epochs of the universe. Galactic bulges represent complex, multifaceted structures that embody the diverse evolutionary pathways of their host galaxies. From classical bulges formed through dramatic merger events to pseudo-bulges built gradually through secular processes, these central structures provide crucial insights into galaxy formation and evolution across cosmic time. Their intimate connection with central supermassive black holes further highlights their importance in understanding the coordinated growth of galactic components. The kinematic properties of bulges, including their rotation patterns and velocity dispersions, offer additional dimensions for classification and analysis, revealing how these structures both influence and are influenced by their host galaxies. As astronomical techniques continue to advance, our understanding of bulge characteristics will undoubtedly deepen, offering ever more detailed views of these fascinating galactic components and their role in shaping the universe as we see it today.